Hello everybody. So here we are here today to talk about Grill, which uses HQL to provide a holistic view over various underlying data warehouses. And I'm here with my colleague here today, Amreshwari. Amreshwari, do you want to introduce yourself?
It's okay. Oops. Yeah. I'm Amareshwari. I work for InMobi. I've been working in Hadoop and ecosystem since 2007. I'm Hadoop PMC and Hive committer. So before that, I was with Yahoo from 2007 to 2011. Yeah, I hand it over to Suma.
Okay, so I'm Suma and I'm an engineer at InMobi and I've been working on data analytics platform since the past 2 years. Prior to this, I was working in Yahoo on data processing and ingestion platforms based on Hadoop. So coming to the agenda for today, we'll be talking about the current state of analytics at InMobi, the problem areas with the current state which motivated us to implement Grill. We'll be talking about why we chose Apache Hive as the SQL interface for Grill and what are the current features that are missing in Hive, one of which is OLAP querying capabilities, which we added as part of this effort, followed by a few query examples with querying OLAP cubes. Then we'll be drilling down into the Grill architecture, followed by a demo. So at InMobi, we are mainly into mobile advertising. So at the core of its business, it provides a marketplace wherein publishers can or app developers can sell real estate on their apps or websites. So the publishers sell this to InMobi and InMobi in turn sells this to advertisers who want to target relevant ads to users. So InMobi relies heavily on analytics to improve on ad relevance and ad targeting on a continuous basis. So let's briefly look at the analytics use cases at InMobi. So I would like to broadly classify users into 3 different categories here. One set of users is the beginners or the naive set of users who are hardly familiar with SQL. They primarily rely on user interface or dashboards for their day-to-day analytics, and they also want to run scheduled queries. So scheduled queries, for example, if you have an advertiser, he would want his report by the end of each business day. So ideally, the query should run daily at a given hour. So the second set of users would be business or product analysts and data scientists, though they are fairly familiar with SQL. And data scientists primarily want to run machine learning algorithms to infer insights from the data through these queries. And these set of users, they generally tend to run ad hoc set of queries because they're constantly trying to improve on ad relevance or add value to the business. Then the third set of users are engineering systems or developers. These users are fairly comfortable with programming and SQL, and they also tend to run ad hoc queries. So ad hoc queries in turn could be interactive or batch oriented in nature. So these are primarily the use cases. So briefly, I would summarize them as canned or dashboard queries, which are limited to a predefined set of measures and dimensions that are pre-known. Then you have ad hoc queries, which are constructed at runtime. And you have interactive and batch queries. Also, people want to schedule their queries to run at a given time. And data scientists want to infer insights through machine learning. So given these use cases, we have 3 different systems at InMobi running analytics for us. One is the ad hoc querying system, which runs on top of HDFS and Hadoop, and it's primarily a batch-oriented system. It has a custom UI and API attached to it. And the second system is a dashboard querying system, which is based out of a columnar data warehouse, and it primarily runs interactive queries. The third system is an external customer-facing system, which is based out of Postgres currently, and it is highly interactive in nature, and it has tight SLAs bound to it. So to summarize the warehouses and the scale at NMOB, you have billions of add requests and impressions per day. We have a 170 terabyte Hadoop warehouse currently, and a 5 TB columnar data warehouse. Our metadata primarily resides on an HBase cluster or DBMS based on Postgres. We intend to use Spark and Shark as an execution engine in the near future. So why do we need both a Hadoop and a SQL warehouse? So typically users are firing canned or dashboard or ad hoc queries. So canned queries typically do IO scans in the range of 10 to hundreds of GBs, and they're fairly interactive in nature with tight SLAs. So we want to serve them out of a columnar data warehouse. And if you have ad hoc queries, they could be interactive or batch oriented in nature based on query complexities and the data volumes that they're querying. Ad hoc queries typically, if they are interactive, they're served out of a columnar warehouse, and if they are batch oriented, they're served out of Hadoop currently. So what are the problems? So these systems on their own, they are able to answer queries with a given acceptable response time, but the various problems associated with this. So you have a disparate user experience because on each system you have different naming conventions for the schema and the names. So users are confused which system they should go to. And users generally, they want to run interactive queries, but they might end up using a batch-oriented system. So they fire a query and they end up waiting for a long time for the query to execute. So there are disparate data storages and execution engines as well, which makes it very hard for one system to leverage data on the other system. And the execution engines are also separate. So this inherently leads to schema management issues for developers who need to manage schema across various systems now for the same set of fields, and also data discovery issues. So we are also not able to leverage SQL on Hadoop innovations out of the box like Impala or Shark, which we wanted to. So we want to fill these gaps by implementing some set of features in Apache Hive and some through Grill. So why we chose Apache Hive? So these are the current features that are available in Apache Hive. It's able to associate structure to the data, and it provides data and schema discovery through Metastore and HCatalog. It is able to provide pluggable storage interface through basically through HBase, HDFS storages or any other. It accepts SQL-like queries and is widely adopted across the community, and it has a wide backing from the Apache community. But what are the features missing in Hive that we added as part of this effort and in Grill? There are data warehouse features like cubes, facts, and dimensions that are missing. We'll be covering more on that in the upcoming slides. Also, you cannot associate a logical table with multiple physical storages. For example, if you have the same table residing in HDFS or a relational database, and you want to serve a query based on the cost from either one of them, you're not able to do that because you're not able to associate this. And you cannot have pluggable execution engines which could seamlessly execute across various data warehouses. Also, it lacks query lifecycle management features like query caching, which is pretty important in order to save cluster, in case your cluster is congested. And also, it doesn't maintain user query history. Another important thing is query quota management, which it lacks. So this is important in case you want to charge back users based on the cluster usage capacity, or you want to guarantee a fair share policy for users based on their current usage. Also, it doesn't support scheduling queries currently. The other thing it lacks is plugging in machine learning models seamlessly that could execute across various data warehouses. So before we delve into how exactly we have implemented the data warehouse features in Apache Hive, we'll be looking at the data layout of a typical OLAP cube. A cube essentially consists of dimensions and measures. So at the base of the cube, you have a raw fact which could consist of hundreds of dimensions and measures. So when you receive a query, you typically wouldn't want to service this out of the raw fact because the IO scans are very expensive. So typically what you do is you generate aggregate facts out of commonly used measures and dimensions, which are a subset of this raw fact. And based on the query access patterns, you would generate multiple raw facts which are able to service most of the query requests. And on the other axis, you want to aggregate these facts based on time. So you could have hourly, daily, monthly granularity facts. And ideally, would like to service the query out of the top of the pyramid because you want to answer the query out of the least set of dimension and measure owning facts. And also a monthly query is cheaper to answer over a monthly fact rather than over, let's say, 30 days of daily facts. Also, a fact is associated with various dimension tables through dimension keys. So this is done at query execution time by joining with various dimension tables. So this is similar to a typical Snowflake schema in a data warehouse. So given this, we will now move into the OLAP model implementation in Apache Hive. So over to Amreshwari.
Yeah, so what we are trying to do is whatever we have seen the data model just now, the pyramid and the Snowflake association, we would like to represent that in Apache Hive. So for this, we add 4 first-class constructs in Hive itself, so which are called like a cube, a storage, a fact table, and a dimension table. So cube is nothing but something containing measures and dimensions, and storage is any physical storage that you have. And the fact table is actually the table. So we'll see more details of this in the coming slides. I'm just giving a brief of what each it is. So and a dimension table is table holding all your attribute data. So and fact table and dimension table can be present on a physical storage. So they are physical fact tables and physical dimension tables. So a cube consists of set of measures and dimensions. Measures are anything that you can measure, and dimension is which is describing your measure. So a measure can be a simple column, which will have things like name, type, and it can have a default aggregate if you look at the pyramid, right? So when you are taking the measure up the pyramid, you have to aggregate it. So you will be associating the measure with a default aggregate on how you are rolling up the pyramid. So you can have an aggregate associated with it, or like what is the start date and end date of the measure, how it is available, or an expression measure where it is actually an expression over already existing measures. A dimension is an attribute which describes a cut on the measure. So it can be a simple dimension with name and type, or a reference dimension. Reference dimension actually references another table on a column. on that, yeah. So similar to your foreign key in RDBMS. Or a hierarchical dimension. So hierarchical dimension is something like location. So you have zip code, city, state, and then country, and then you have region. So that all that can be a hierarchical dimension as a single dimension, and user can give any of that. And then again, expression dimension, which is an expression over existing dimensions, or a time dimension where user can actually give time range for the dimension. So some of these concepts are actually taken from Mondrian. I'll just go over the next one. So the storage will have a name and an endpoint and some properties. For example, the prod cluster and what is its name node endpoint, or a HBase cluster and what is its endpoint, or a Postgres DB and what is the server, where is it running. Fact table is actually the table where you have set of columns. So it is more than the table that you will say actually which cube the fact belongs to. And you will also say storages on which it is present and the update periods. So I'll tell you more on this. So a fact table that we have described, right? So you are saying that I am defining a fact with 10 measures and 10 dimensions, and that can be present on, say, 2 storages. So, and one storage you might want to keep hourly updates, other storage you might want to keep daily updates. So you'll say that, okay, I want to keep this fact on storage 1 with hourly and storage 2 with daily updates. So a fact belongs to a cube, and cube will have multiple facts. That is the relationship that it shows. And then fact table is present on the storage. So going to dimension table. So dimension table is again table, which is usually slow changing data. So fact table is something that doesn't change. Once it is there, it doesn't change. But dimension table is a changing one. So it will have columns, and it can have again references to other tables. So you'll define dimension references, and then storages on which it is present. So if you're dumping your dimension table on like file system, so you will be dumping with some snapshot periods. So you may associate a file system like storage with a snapshot dump period if there is any. Otherwise, it can be directly available on the storage like HBase or a DB. So if you look at the relationship between cube and dimension tables, so cube referred to dimension tables, and dimension tables can refer to other dimension tables. And dimension tables are present on storage. So a storage table is the final physical storage table, which can be either a fact table or dimension table. So this will have the final storage descriptor. So fact table or dimension table are still logical tables what we have seen. So there you will only specify the schema and you will not say how it is stored. For example, here I am defining one storage table which is for the fact, which is for aggregate fact 1, and which is stored as RC file. Or I can have another storage descriptor which is saying it is stored as a text file or ORC file, things like. So, and storage table will be partitioned by columns. Yeah, so whatever partition columns that you have in Hive, you will be using that here. And this table has a naming convention which says that storage name is followed by the fact name or dimension table, so that like it will figure out which storage table it has to pick up at the runtime. So, and each partition can override its storage descriptor as it is already available in Hive. So you have fact tables and dimension tables, finally, which have the storage tables. So if we look at our pyramid back, so the whole pyramid is actually the cube, and then each box there is the fact table. And then each blue box here is the dimension table. So we'll see some examples. Yeah, before that I'll just go through the grammar for the example, for the query. So it is HiveQL with just one more construct as cube in the starting, and there is something called time range in with the column name and a from and to for the date range that you want to give. So it has like select from, where, group by, having, order by, limit, all others as HiveQL, and two more added to it. So this is detailed description of the grammar. That is for completeness, I put it. So you can go through that if you required. So, so what will happen if a query like cube select something comes, right? So it will resolve which are the candidate tables that can answer the query and the storages, and then automatically resolve joins, because when we specified our schema, we told all the relationships. So you need not, in your query, you need not always give join on your condition. So it will figure out the join for you. And then resolve aggregates and group by expressions, because default aggregate is given for the measure. And it allows complicated SQL over the QL language that we have just seen. And queries can spawn multiple storages as well. And it can accept multiple time range queries as well. And all other HiveQL features come for you, all UDFs and UDFs. So we'll see a simple example. So here, this is a cube select query with name and, so this is a dimension table query where we are selecting name and state ID from city table with limit of 100. So this is what user is giving, but he doesn't know where actually city table is present. So city table is present in two storages. One is a storage, say C2, on which it is actually HBase cluster. Our other is HDFS, is C1, and which is dumped early. So, so here is an example of a rewrite of this. So what this engine will do is like it will rewrite the query to say that okay, it is picking up C2 city table to answer this query, or it is picking up C1 city table where the partition is latest. We'll see one more query. So here we are saying that give me city table, for each city, get me measure 2 from test cube for 2 days, where time range is for 2 days. So if we look at this, so this has been rewritten to pick up actual physical fact table and the dimension tables, and it has figured out which partitions to pick up. So it is figured out what is the aggregate here, and also the join condition for between city and the test cube, and then it has picked up some hourly partitions and a daily partition, because the 2-day range is including some hours of the previous day and some hours of the today and a day in between. So it has picked up hourly for like 10th March 3rd hour to 23rd hour and 11th March, and then 12th March till 2nd hour. So it will figure out like whether it has to pick up daily partitions or hourly partitions depending on that. Yeah. So we have seen like data warehousing features and the logical table association. So this is all available in Hive directly. And now we'll see what is available as Grill. So pluggable execution engine for the HQL that we have, and then the query lifecycle management and scheduling. So once we have the rewritten HQL for the cube query, actually that HQL can be given to anyone who understands HiveQL. So HiveQL is understood not just by Hive, but other execution engines as well, like Impala or Shark, right? And it is very similar to SQL. So if we maybe just like replace some things that SQL doesn't have, then we can give it to any SQL engine as well. So we'll see more on Grill. Yeah, so Grill wants to actually unify both catalog and query layer for all the things that Suma mentioned, that ad hoc and canned queries or batch and interactive reports and a single interface. So here is the simple architecture of it. So if you look at the data stores, you have like HDFS, HBase, or a columnar data warehouse, or S3 or Redshift. So if you have figured out your data warehouse, what are your fact tables and dimension tables, so you can keep like all your monthly data and yearly data in HDFS. Actually, the whole data in HDFS, but you might want to keep some frequently used data in a columnar data warehouse where it will be answered faster, right? So, and then Grill will figure out like if your query is going to fall in the range of last 1 week and that is there in columnar data warehouse, it will figure out that storage and rewrite the query for you. If it is not in the columnar data warehouse, it will go to the HDFS. So for executing the query on HDFS, it would use Hive, but for executing on a columnar data warehouse, it will directly use a JDBC driver. So, or you can write any other drivers also here, like Shark or Impala or anything, Redshift driver. So, yeah, so Grill server exposes mainly the REST API for all the things like for Metastore and query service. And then, so there have been we have clients built on top of it like CLI, Java client, and JDBC. And then all of the Metastore is present in Hive Metastore itself. Yeah, so that completes that. So if we have to write a new execution engine, we just have to implement the interface which says like explain your query, which gives a cost to it, or and execute the query, or execute asynchronously, and fetch results from that engine, and specify all the storages that it can support. So how the execution engine is linked to the storage is like, you will say in case of Hive, it would say that I support HDFS and HBase and S3. And maybe JDBC driver would say that I support columnar driver, columnar DWH, and also Redshift, if Redshift works on JDBC, right? Or another MySQL or Postgres. So, each driver would say like what are all the storages it can support. So if there is a new driver which can support all of them, then like that driver can be used to run all the queries. So if a cube query with if cube query comes with multiple execution engines, then what is done is like we'll rewrite the query for each execution engine for the supported storages, and then get cost for the rewritten query for each of the engine, and then pick up the one with least cost. So if the storage, if one of the engine doesn't have it on its storage, then its cost will be like infinite and it will not be chosen, right? So yeah, so I'll get into more into the Grill server. So Grill server has Jack Saras as the REST API that users can come, and it has like authentication, authorization metrics, and then it has scheduling service where users go schedule queries to run, say, every month, every first of the month, or every first of the week, or first day of the week, every Monday of the week. Or query service where they submit queries and look at it or kill it, or look at their history, who is running, who has run most number of queries, all that you can look at. And then a Metastore service where you can browse your Metastore, and a session service where it provides you a session like MySQL shell. So you open a session, you add jars to it, you set some configuration parameters, and then run queries. So those are available throughout the session. Yeah. So and then you have Hive, JDBC, and Impala drivers. And all of these services interact through events. So there is an event service as well. So what is the current state of the grill? So query service is up, is there. And then we have Metastore service completed, and then metrics. And query statistics is in progress. Query statistics are mainly useful for you to actually decide which are the columns that are being queried often, so that like you can actually move them up your pyramid if that is queried properly. So and then scheduled queries is you want to schedule them first of the week. And then query caching, if the same query comes, return the results immediately. So those are in progress, should be complete within a month. And then on the client side, we have Java client and CLI and JDBC client ready. And then from the execution engine side, we have Hive driver and JDBC driver and Impala driver ready. So on the grill roadmap, what we have is to normalize the query cost across execution engines, and then and load balancing across execution engines. Actually, even if the cost is lower on one of the execution engines, but if it is busy, query can be executed in the other execution engine. So that is one more. And then alter meta hooks in the Hive storage handler. So this is basically to, so whenever a table is altered a fact table is altered, it has to be altered all the way down to on all the storages. So if it is by a DB storage handler, where it is actually backed up by a DB storage, it has to go alter the table and DB. That gives the flexibility of the user to just go do one alter, which he doesn't need to go care about, like change it in all the DBs, change it in all the clusters, right? So we need to have alter meta hooks for that, and then authentication and authorization, and then machine learning through grill, and then quota management. So these are all in the roadmap. We'll take them up. So here are some statistics at InMobi. So number of queries run per day are like 700 to 900 per day. And then we have around 125 dimension tables, 30 fact tables, and 22 cubes. And the size is like 170 and 400 MB. Here are some references on this work. So there is a Jira Hive 4115 where all the OLAP cubes are described. And then, so all the code is committed in GitHub InMobi Hive right now. And then the grill code is available in GitHub InMobi grill, and all the documentation is also available, and mailing lists are open. We'll do a demo. We have 5 minutes. So I'll bring up a grill server. Server is up. I need to increase the font. This is clear. Okay, so if we open a CLI here, it will open a session with the grill server. So These are all the commands we have. So currently there are no cubes, no dimensions. So we'll like create some. I'll quickly run an example so that all the meta store is populated. So I'm creating a sample meta store. Excuse me. And then populate. So there are 3 tables, 3 dimensions created, and then show. So there are 3 storages created. There is cluster 1, local, and MyDB. So there is sample cube. So describe dimension. So this is the dimension table where it has like some columns, and it has a reference like D2 ID is referring to dim table 2 on ID, and it is available on local storage with hourly update. If we describe storage, say MyDB. So this is a DB storage, and the DB storage URL is /temp with DB storage DB. So if you look at local, local is a HDFS storage with storage URL as file colon. So we'll do query execute. So we are doing execute on cube select from dim table. So this will be because dim table is present on local, so it will be using Hive to execute the query. So that is it's taking time. So it gave some result, right? So we will describe dim table 3. This is present on DB. Storage name is MyDB. So we'll run the query on MyDB. So this will be launching through the JDBC driver, which will connect to the DB and get fetch results from the DB here. So this for this we are using like all local setup, like local Hadoop, local job runner, and local Hive, and the DB is SQLite DB we are using. So this has come in 1 second, and the other one has like took 8 seconds. Yeah, so that is what I have. Any questions?
I guess in some cases where like your final result would be the aggregation of those results. So where the aggregation actually happens, it happens at the client or at the, basically you have results, partial result from one execution engine, some other result from another execution engine. How do you get those consolidated to the final result?
No, it doesn't fetch from 2 engines. It will choose 1 engine and only that will give the results. It doesn't combine results from 2 places.
But what if my query is across different storages?
So the execution engine has to support different storages. For example, HDFS and HBase, they are engines which support. So if there is a new engine which supports DB and also HDFS, then that engine would be used to answer if that is what you wanted. But this is not doing any, there is no execution engine in Grill itself. So this is only unifying them and giving a single interface.
I see, thank you.
Any more questions?
Hi. So how do you deal with count distinct dimensions because with regard to aggregating over time, because you can't, because if it's a distinct, you can't just sum it just straightforwardly?
So distinct queries have to go to the raw fact that we have. So if you looked at the pyramid, so we had the raw in the end, so which is not aggregated on any dimension. So such queries will just hit the bottom of the pyramid and it might take time to come out. But yeah.
Do you have like support for like a particular table that it knows it's pre-aggregated by that distinct quality?
Pardon? Can you repeat?
No,
Can you repeat?
no, never mind. Thank you.
Can you repeat? No? Oh, okay. Sorry.
Any more questions? Okay, thank you. That's the end of our session.